Welcome to the I Can't Sleep podcast, where I help you drift off one fact at a time. I'm your host, Benjamin Boster, and today's episode is about Flint. Make sure to follow the show so you never miss an episode. Flint, occasionally flint stone, is a sedimentary cryptocrystalline form of the mineral quartz, categorized as the variety of chert that occurs in chalk or marley limestone. Historically, flint was widely used to make stone tools and start fires. Flint occurs chiefly as nodules and masses in sedimentary rocks, such as chalks and limestones. Inside the nodule, flint is usually dark gray or black, green, white, or brown in color, and has a glassy or waxy appearance. A thin oxidized layer on the outside of the nodules is usually different in color, typically white and rough in texture. The nodules can often be found along streams and beaches. Flint breaks and chips into sharp-edged pieces, making it useful in constructing a variety of cutting tools, such as knife blades and scrapers. The use of flint to make stone tools dates back more than 3 million years. Flint's extreme durability has made it possible to accurately date its use over this time. Flint is one of the primary materials used to define the Stone Age. During the Stone Age, access to flint was so important for survival that people would travel or trade long distances to obtain the stone. Grimes Graves was an important source of flint traded across Europe. Flint Ridge in Ohio was another important source of flint, and Native Americans extracted the flint from hundreds of quarries along the ridge. This Ohio flint was traded across the eastern United States and has been found as far west as the Rocky Mountains and south around the Gulf of Mexico. When struck against steel, flint will produce enough sparks to ignite a fire with the correct tinder or gunpowder used in weapons, namely the flintlock firing mechanism. Although it has been superseded in these uses by different processes, the percussion cap, or materials, ferrocerium, flint has lent its name as generic term for a fire starter. The exact mode of formation of flint is not yet clear, but it is thought that it occurs as a result of chemical changes in compressed sedimentary rock formations during the process of diagenesis. One hypothesis is that a gelatinous material fills cavities in the sediment, such as holes bored by crustaceans or mollusks, and that this becomes silicified. The hypothesis would certainly explain the complex shapes of flint nodules that are found. The source of dissolved silica in the porous media could be the spicules of siliceous sponges, demosponges. Certain types of flint, such as that from the south coast of England and its counterpart on the French side of the Channel, contain trapped fossilized marine flora. Pieces of coral and vegetation have been found preserved inside the flint, similar to insects and plant parts within amber. Thin slices of the stone often reveal this effect. Flint sometimes occurs in large flint fields, in Jurassic or Cretaceous beds, for example, in Europe. Puzzling giant flint formations known as paramudra and flint circles are found around Europe, but especially in Norfolk, England, on the beaches at Beeston Bump and West Runton. The Ohio flint is the official gemstone of Ohio State. It is formed from limey debris that was deposited at the bottom of inland Paleozoic seas hundreds of millions of years ago, that hardened into limestone and later became infused with silica. The flint from Flint Ridge is found in many hues, like red, green, pink, blue, white, and gray, with the color variations caused by minute impurities of iron compounds. Flint can be colored: sandy brown, medium to dark gray, black, reddish brown, or an off-white gray. Flint was used in the manufacture of tools during the Stone Age, as it splits into thin, sharp splinters called flakes or blades, depending on the shape, when struck by another hard object, such as a hammerstone made of another material. This process is referred to as knapping. Flint mining is attested since the Paleolithic, but became more common since the Neolithic. In Europe, some of the best tool-making flint has come from Belgium, the coastal chalks of the English Channel, the Paris Basin, too, in Jutland, flint mine at Hove, the Sannonian deposits of Ruchen, Grimes Graves in England, the upper Cretaceous chalk formation of Dobruja, and the lower Danube, Balkan flint, the Cenomanian chalky marl formation of the Moldavian Plateau, and the Jurassic deposits of the Krakow area and Chemionki in Poland, as well as the Legern silex in the Jura Mountains of Switzerland. In 1938, a project of the Ohio Historical Society under the leadership of H. Holmes Ellis began to study the knapping methods and techniques of Native Americans. Like past studies, this work involved experimenting with actual knapping techniques by creation of stone tools through the use of techniques like direct freehand percussion, freehand pressure, and pressure using a rest. Other scholars who have conducted similar experiments and studies include William Henry Holmes, Alonzo W. Pond, Francis H. S. Knowles, and Don Crabtree. To reduce susceptibility to fragmentation, flint chert may be heat-treated, being slowly brought up to a temperature of 150 to 260 degrees Celsius for 24 hours, then slowly cooled to room temperature. This makes the material more homogeneous, and thus more knappable, and produces tools with a cleaner, sharper cutting edge. Heat treating was known to Stone Age artisans. When struck against steel, a flint edge produces sparks. The hard flint edge shaves off a particle of the steel that exposes iron, which reacts with oxygen from the atmosphere and can ignite the proper tinder. Prior to the wide availability of steel, rocks of pyrite would be used along with the flint in a similar but more time-consuming way. These methods remain popular in woodcraft, bushcraft, and amongst people practicing traditional fire-starting skills. A later major use of flint and steel was in the flintlock mechanism, used primarily in flintlock firearms, but also used on dedicated fire-starting tools. A piece of flint held in the jaws of a spring-loaded hammer, when released by a trigger, strikes a hinged piece of steel, frizzen, at an angle, creating a shower of sparks and exposing a charge of priming powder. The sparks ignite the priming powder, and that flame in turn ignites the main charge, propelling the ball, bullet, or shot through the barrel. While the military use of the flintlock declined after the adoption of the percussion cap from the 1840s onward, flintlock rifles and shotguns remain in use amongst recreational shooters. Flint and steel used to strike sparks were superseded in the 20th century by ferrocerium, sometimes referred to as flint, although not true flint, mish metal, hot spark, metal match, or fire steel. This human-made material, when scraped with any hard, sharp edge, produces sparks that are much hotter than obtained with natural flint and steel, allowing use of a wider range of tinders. Because it can produce sparks when wet and can start fires when used correctly, ferrocerium is commonly included in survival kits. It is used in many cigarette lighters where it is referred to as a flint. Flint's utility as a fire starter is hampered by its property of uneven expansion under heating, causing it to fracture, sometimes violently during heating. This tendency is enhanced by the impurities found in most samples of flint that may expand to a greater or lesser degree than the surrounding stone, and is similar to the tendency of glass to shatter when exposed to heat, and can become a drawback when flint is used as a building material. Flint, napped or unnapped, has been used from antiquity, for example at the late Roman fort of Burgh Castle in Norfolk, up to the present day as a material for building stone walls, using lime mortar, and often combined with other available stone or brick rubble. It was most common in those parts of southern England where no good building stone was available locally, and where brick-making was not widespread until the later Middle Ages. It is especially associated with East Anglia, but also used in chalky areas stretching through Hampshire, Sussex, Surrey, and Kent to Somerset. Flint was used in the construction of many churches, housing, and other buildings. For example, the large stronghold of Framlingham Castle. Many different decorative effects have been achieved by using different types of napping or arrangement and combinations of stone flushwork, especially in the 15th and early 16th centuries. Because napping flints to a relatively flush surface and size is a highly skilled process with a high level of wastage, flint finishes typically indicate high-status buildings. Flint pebbles are used as the media in ball mills to grind glazes and other raw materials for the ceramics industry. The pebbles are hand-selected based on color. Those having a tint of red, indicating high iron content, are discarded. The remaining blue-gray stones have a low content of chromophoric oxides, and so are less deleterious to the color of the ceramic composition after firing. Until recently, calcined flint was also an important raw material in clay-based ceramic bodies produced in the UK. In clay bodies, calcined flint attenuates the shrinkage while it's drying and modifies the fired thermal expansion. Flint can also be used in glazes as a network former. In preparation for use, flint pebbles, frequently sourced from the coast of southeast England or western France, were calcined to around 1,000 degrees Celsius. This heating process both removed organic impurities and induced certain physical reactions, including converting some of the quartz to cristobalite. After calcination, the flint pebbles were crushed and milled to a fine particle size. However, the use of flint has now been superseded by quartz. Because of the historical use of flint, the word flint is used by some potters, especially in the U.S., to refer generally to silicious raw materials used in ceramics that are not flint. Flint bracelets were known in ancient Egypt, and several examples have been found. Quartz is a hard crystalline mineral composed of silica, silicon dioxide. The atoms are linked in a continuous framework of SiO4, silicon oxygen tetrahedra, with each oxygen being shared between two tetrahedra, giving an overall chemical formula of SiO2. Quartz is therefore classified structurally as a framework silicate mineral and compositionally as an oxide mineral. Quartz is the second most abundant of the minerals and mineral groups that compose the Earth's lithosphere, with the feldspars making up 41% of the lithosphere by weight, followed by quartz making up 12%, and the pyrazines at 11%. Quartz exists in two forms, the normal alpha quartz and the high-temperature beta quartz, both of which are chiral. The transformation from alpha quartz to beta quartz takes place abruptly at 573 degrees Celsius. Since the transformation is accompanied by a significant change in volume, it can easily induce microfracturing of ceramics or rocks passing through this temperature threshold. There are many different varieties of quartz, several of which are classified as gemstones. Since antiquity, varieties of quartz have been the most commonly used minerals in the making of jewelry and hard stone carvings, especially in Europe and Asia. Quartz is the mineral defining the value of 7 on the Mohs scale of hardness, a qualitative scratch method for determining the hardness of a material to abrasion. The word quartz is derived from the German word Quarz, which had the same form in the first half of the 14th century in Middle High German and in East Central German, and which came from the Polish dialect term twarda, which corresponds to the Czech term tvrdy, hard. Some sources, however, attribute the word's origin to the Saxon word kverklufterz, meaning cross-vein ore. The ancient Greeks referred to quartz as kristallos, derived from the ancient Greek kryos, meaning icy cold, because some philosophers understood the mineral to be a form of supercooled ice. Today, the term rock crystal is sometimes used as an alternative name for transparent, coarsely crystalline quartz. Roman naturalist Pliny the Elder believed quartz to be water ice, permanently frozen after great lengths of time. He supported this idea by saying that quartz is found near glaciers in the Alps, but not on volcanic mountains, and that large quartz crystals were fashioned into spheres to cool the hands. This idea persisted until at least the 17th century. He also knew of the ability of quartz to split light into a spectrum. In the 17th century, Nicolaus Steno's study of quartz paved the way for modern crystallography. He discovered that regardless of a quartz crystal's size or shape, its long prism faces always joined at a perfect 60-degree angle, thus discovering the law of constancy of interfacial angles. Quartz belongs to the trigonal crystal system at room temperature and to the hexagonal crystal system above 573 degrees Celsius. The former is called alpha quartz The latter is beta quartz. The ideal crystal shape is a six-sided prism, terminating with six-sided pyramid-like rhombohedrons at each end. In nature, quartz crystals are often twinned, with twin right-handed and left-handed quartz crystals, distorted, or so intergrown with adjacent crystals of quartz or other minerals as to only show part of this shape, or to lack obvious crystal faces altogether and appear massive. Well-formed crystals typically form as a druse, a layer of crystals lining a void, of which quartz geodes are particularly fine examples. The crystals are attached at one end to the enclosing rock, and only one termination pyramid is present. However, doubly terminated crystals do occur where they develop freely without attachment, for instance within gypsum. Alpha quartz crystallizes in the trigonal crystal system, space group P3 sub 1 21, or P3 sub 2 21, space group 152 or 154 respectively, depending on the chirality. Above 573 degrees Celsius, alpha quartz in P3 sub 1 21 becomes the more symmetric hexagonal P6 sub 422, space group 181. And alpha quartz in P3 sub 2 21 goes to space group P6 sub 2 22, number 180. These space groups are truly chiral. They each belong to the 11 enantiomorphous pairs. Both alpha quartz and beta quartz are examples of chiral crystal structures composed of achiral building blocks, SiO4 tetrahedra in the present case. The transformation between alpha and beta quartz only involves a comparatively minor rotation of the tetrahedra with respect to one another, without a change in the way they are linked. However, there is a significant change in volume during this transition, and this can result in significant microfracturing and ceramic strain firing, in ornamental stone after a fire, and in rocks of the Earth's crust exposed to high temperatures, thereby damaging materials containing quartz and degrading their physical and mechanical properties. Although many of the varietal names historically arose from the color of the mineral, current scientific naming schemes refer primarily to the microstructure of the mineral. Color is a secondary identifier for the cryptocrystalline minerals, although it is a primary identifier for the macrocrystalline varieties. The most important microstructure difference between types of quartz is that a macrocrystalline quartz, individual crystals visible to the unaided eye, and the microcrystalline or cryptocrystalline varieties, aggregates of crystals visible only under high magnification. The cryptocrystalline varieties are either translucent or mostly opaque, while the macrocrystalline varieties tend to be more transparent. Chalcedony is a cryptocrystalline form of silica consisting of fine intergrowths of both quartz and its monoclinic polymorph mogonite. Agate is a variety of chalcedony that is fibrous and distinctly banded with either concentric or horizontal bands. While most agates are translucent, onyx is a variety of agate that is more opaque, featuring monochromatic bands that are typically black and white. Carnelian or sard is a red-orange translucent variety of chalcedony. Jasper is an opaque, chert, or impure chalcedony. Pure quartz, traditionally called rock crystal or clear quartz, is colorless and transparent or translucent, and has often been used for hard stone carvings, such as the Lothair crystal. Common colored varieties include citron, rose quartz, amethyst, smoky quartz, milky quartz, and others. These color differentiations arise from the presence of impurities, which change the molecular orbitals, causing some electronic transitions to take place in the visible spectrum causing colors. Amethyst is a form of quartz that ranges from a bright, vivid violet to a dark or dull lavender shade. The world's largest deposits of amethyst can be found in Brazil, Mexico, Uruguay, Russia, France, Namibia, and Morocco. Amethyst derives its color from traces of iron in its structure. Ametrine, as its name suggests, is commonly believed to be a combination of citrine and amethyst in the same crystal. However, this may not be technically correct. Like amethyst, the yellow quartz component of ametrine is colored by iron oxide inclusions. Some, but not all, sources define citrine solely as quartz with its color originating from aluminum-based color centers. Other sources do not make this distinction. In the former case, the yellow quartz in ametrine is not considered true citrine. Regardless, most ametrine on the market is in fact partially heat or radiation-treated amethyst. Blue quartz contains inclusions of fibrous magnesio-riebeckite or chrysotillite. Inclusions of the mineral dumortierite within quartz pieces often result in silky-appearing splotches with a blue hue. Shades of purple or gray sometimes also are present. Dumortierite quartz, sometimes called blue quartz, will sometimes feature contrasting light and dark color zones across the material. Blue quartz is a minor gemstone. Citrine is a variety of quartz whose color ranges from yellow to yellow-orange or yellow-green. The cause of its color is not well agreed upon. Evidence suggests the color of citrine is linked to the presence of aluminum-based color centers in its crystal structure, similar to those of smoky quartz. Both smoky quartz and citrine are dichroic in polarized light, and will fade when heated sufficiently or exposed to UV light. They may occur together in the same crystal as smoky citrine. Smoky quartz can also be converted to citrine by careful heat treatment. Alternatively, it has been suggested that the color of citrine may be due to trace amounts of iron, but synthetic crystals grown in iron-rich solutions have failed to replicate the color or dichroism of natural citrine. The UV sensitivity of natural citrine further indicates that its color is not caused solely by trace elements. Natural citrine is rare. Most commercial citrine is heat-treated amethyst or smoky quartz. Amethyst loses its natural violet color when heated to above 200 to 300 degrees Celsius, and turns a color that resembles natural citrine, but is often more brownish. Unlike natural citrine, the color of heat-treated amethyst comes from trace amounts of the iron oxide minerals hematite and goethite. Clear quartz with natural iron inclusions or limonite staining may also resemble citrine, but it's not true citrine. Like amethyst, heat-treated amethyst often exhibits color zoning, or uneven color distribution throughout the crystal. In geodes and clusters, the color is usually deepest near the tips. This does not occur in natural citrine. It is nearly impossible to differentiate between cut citrine and yellow topaz visually, but they differ in hardness. Brazil is a leading producer of citrine, with much of its production coming from the state of Rio Grande do Sul. The name is derived from the Latin word citrina, which means yellow, and is also the origin of the word citron. Citrine has been referred to as the merchant stone or money stone due to a superstition that it would bring prosperity. Citrine was first appreciated as a golden yellow gemstone in Greece between 300 and 150 BC during the Hellenistic Age. Yellow quartz was used prior to that to decorate jewelry and tools, but it was not highly sought after. Milky quartz is the most common variety of crystalline quartz. The white color is caused by minute fluid inclusions of gas, liquid, or both, trapped during crystal formation, making it of little value for optical and quality gemstone applications. Rose quartz is a type of quartz that exhibits a pale pink to rose-red hue. The color is usually considered due to trace amounts of titanium, iron, or manganese in the material. Some rose quartz contains microscopic rutile needles that produce asterism in transmitted light. Recent X-ray diffraction studies suggest that the color is due to thin microscopic fibers of possibly dumortierite within the quartz. Additionally, there is a rare type of pink quartz, also frequently called crystalline rose quartz, with color that is thought to be caused by trace amounts of phosphate or aluminum. The color in crystals is apparently photosensitive and subject to fading. The first crystals were found in a pegmatite found near Rumford, Maine in the U.S., and in Minas Gerais, Brazil. The crystals found are most transparent and euhedral due to the impurities of phosphate and aluminum that formed crystalline rose quartz, unlike the iron and microscopic dumortierite fibers that formed rose quartz.